So today I'm going to talk about waves in layered media. This is a rather important topic. I'm going to talk about generalized reflection coefficient for layered medium. We have heard of the term generalized reflection coefficient for transmission line theory. So we would exploit knowledge from transmission line theory to understand generalized reflection coefficient. And then we do a number of physical interpretation things. The next topic that we like to study is the phase and group velocity, wave guidance in layered medium, and so on. So let's get started. So waves in layered media is actually a very important topic. It was first studied by Sommerfeld when he wanted to understand the propagation of radio wave over the good Earth. He was essentially interested in this topic, that if the Earth is layered, that if you have a radio station, and then if you send radio waves, he knows that above him there's an ionosphere. So how would waves propagate in a layered medium of the Earth and the ionosphere? And Sommerfeld did solve this problem around the turn of the century, I believe, about maybe 1901 or 1902. So we studied this problem now. It has been regurgitated so many times so that we can actually use transmission line theory to help simplify the presentation of this problem. The problem on the top is the case when you send in a wave. This could be a plane wave. The plane waves get reflected and multiply reflected inside the layered medium and finally get transmitted. And we want to find this reflected wave at the top as well as the transmitted wave at the bottom. So you can reorient the top figure to look like this, where you send in the wave in this direction and then look for the reflected wave. I've taken this figure out of Kong's book, so the axes are slightly different in terms of labels. Usually I like to label this as a z-axis, not the x-axis. And this is another picture I took out of Kong's book, where he used a transmission line equivalence to show that this problem I have over here, okay, can be solved as a transmission line problem at the bottom. And I like to show you how, okay? So before we do that, let's use a blank slide to illustrate this. So we have shown that when you have a transmission line, especially multi-section transmission line, that if you have just a single junction transmission line, you can find the reflection coefficient gamma 1, 2, which is something like Z1. Maybe I can say that if this is Z01, this is Z02, it'll be Z01 minus Z02 over Z01 plus Z02. I believe that the minus sign should be here, because when I make Z02 equal to 0, I should get a negative reflection coefficient. We can say that this problem is homomorphic. Okay, we use the concept of homomorphism. That this actually is the same problem as this problem, that if you have a plane wave coming in and then a plane wave transmitted, the two problems can be made to be identical mathematically. Hence, you can also write down a reflection coefficient. For instance, for the TE case, that the reflection coefficient is mu 2 beta 1z minus mu 1 beta 2z over mu 2 beta 1z plus mu 1 beta 2z. Okay, and If you know the single interface reflection coefficient, we have seen that in transmission line theory, you can actually write down the reflection coefficient for, say, a multi-section transmission line. Okay, let me say that you can actually have as many sections as you like. You can actually even put a section here if you want. So if you know the local reflection coefficient gamma 1, 2, say this is 1, 2, 3, 4, and if you know the local reflection coefficient at this junction, then you can build up the generalized reflection coefficient, which says that gamma 1, 2 generalized at the 1, 2 junction is equal to the local reflection coefficient gamma 1, 2 plus gamma 2, 3. Gamma 2, 3 is generalized reflection coefficient at the second junction. So I would have something like 2j beta 2z L2. Let's assume that the second line has a length of L2. Okay. And then the denominator is 1 plus gamma 1, 2, gamma 2, 3 tilde e to the minus 2 j beta 2z L2. We found this to be the generalized reflection coefficient for gamma 1, 2. At this junction, we can define the reflection coefficient. At that junction, we can imagine an incident wave coming in and the reflected wave going back. Since this is time harmonic signal, the reflected wave would include waves that are multiply reflected in the junction in this manner. So this gamma 1, 2 tilde is the generalized reflection coefficient at this junction, including all the multiple reflections from behind the first junction. Okay, so using the same concept, we can say that if we have now say a layered medium where we put in more than one layer, then the wave will bounce back in this manner. And then you can define a generalized reflection coefficient for the 1, 2 interface. Let's say that this is medium 1, 2, and 3. R1, 2 tilde then would be the R1, 2, the local reflection coefficient of first junction, plus R2, 3 tilde e to the minus 2j. I can put in a beta 2z here because the wave number is a number in a z direction. Okay, and then they can say that this thickness here is L2, for instance. And beta 2z is the wave number in that region. So I'm using mathematical parallelism or mathematical homomorphism to write down the solution here. Okay, this is a 3. E to the minus 2j beta 2z L2. Okay, so this is medium 1, 2, and 3. And R2 tilde is a generalized reflection coefficient because I could have multiple reflection coming from behind the 2, 3 interface as well. So the waves from a layered medium can be solved rather easily using this concept. Are there any questions regarding this concept of using mathematical homomorphism or mathematical parallelism to solve the problem of a layered medium by understanding the wave of the transmission line problem? Okay. So if there are no questions, then we will go through doing some ray series interpretations such as this one over here. We can show that if you have a layered medium, if you can write the reflection coefficient like what we have done in the previous slide, you can actually expand this reflection coefficient into a ray series and understand each of the term physically as one of these rays that bounce around like this. So to do this, what we need to do then is to actually take the generalized reflection coefficient and write it as R12 plus R12 tilde. So sorry, this is R23 tilde. Okay, e to the minus 2j beta 2z L2. And then we will have to add and subtract the term in the numerator. The term that we have to add and subtract is actually this term over here, which is R12 tilde, not tilde, R12, R23. Okay, e to the minus 2j beta 2z L2. And I'm going to remove the tildes because I only have two layers here, two interfaces, so that there's no multiple reflection beyond region 3. And because I have to add this, I have to subtract it out to make it equal to before. Because I've subtracted out. I will have something like this. So this is my numerator. Denominator remains the same. It will be the same as before, 1 plus R12, R23, e to the minus 2j beta 2z L2. Remember that I removed my tilde because I don't have a reflection from this layer anymore in this picture. So the R23 tilde goes away, and these are the entire numerator. And I'm going to do some regrouping. I'm going to do some regrouping because I see that this term has an R12. I'm going to regroup it with the first term. I'm sorry, I should have a square here. Okay, I should have a square here because I have the square that I have added in, and then I should have it regrouped with the first thing. And then, so if I put this together with the first term, okay, what I have then is the fact that the first two terms, the first term and this term that I have added in can be written as R12, 1 plus R12, R23, e to the minus 2j, beta 2z L2, okay? And then what is left behind is what I have as, I don't know if you can see that it will be 1 minus R12 square, R23, e to the minus 2j beta 2z L2 divided by the denominator. Can you see it? Okay, what I have done is actually group this term together with this term and factor out the R23 e to the minus 2j beta 2z L2 and put it on the outside. And what I have left is just 1 minus R12. And if I do this, then I notice that things somewhat simplifies because, let me see, move this further down. That this term in the denominator will cancel this term, okay? And I would have just R12 for the first term. And then for the second term, I'm going to write, I'm going to use the fact that this can be factorized. 1 minus R12 square can be written as 1 plus R12 times 1 minus R12. Okay. And I also use the fact that if you look at the Fresnel reflection coefficient, I can write this as T12. Okay. But this is actually minus R21. Okay, I can use the property of Fresnel reflection coefficient if you go back and look at them again. If you have R12, it turns out to be that. If you were to swap the two indices R21, it would just change the sign and make this into negative R12. Okay, so I can hence change this R12 to negative R21. And then this would just be T21. Okay, so this becomes T21, this becomes T12. And then what I have left is something like T12, T23, 21, sorry, 21, R23, e to the minus 2j beta 2z L2 divided by the same denominator. Beta 2z L2. Okay, so you have this now. But the next thing you can do is actually to, let me insert the new slide. I have to make this into blank. What I can do next is actually to use the fact that this denominator that I have over there, that anything like 1 over 1 minus x can be written as 1 plus x squared plus x cubed plus x fourth. Okay, something like this can be written as an infinite power series. So I can think of this as something like 1 minus x, and then expand this as a power series. And if I do that, then I will have terms like that. And then I will not go into the details. Okay, I will not go into the details. But then if you go through identifying this power series, is done in the lecture notes, that each of this term can be physically interpreted as such. For instance, if I just look at the first term is just this reflected term. Okay, and if I look at the next term will be this being set to 1. Okay, it would be T12, which is this coefficient here. Okay, and then the wave travels to interface 2, 3 and suffers a reflection coefficient R23, and then it travels another distance. So the total distance traveled by the wave is 2j beta 2z L2. So it gains a phase factor, which is given by this. And then finally, when it emerges again, it becomes this way because it has to go through a T21 over here. So you can taste this ray series one by one. The first ray series will be this, and then you go to the next term, you will trace the next ray series and so on. Okay, so this is the ray series interpretation of the generalized reflection coefficient, which comes in useful in many works. Okay, are there any questions regarding this? So I will not do the substitution, but if you substitute in, you will see this ray series picture coming out. Okay. So sometimes you see echoes coming from a layered medium. What it says is that when you have a layered medium, you don't see a single reflected ray. You will see a single reflected ray from the first interface, and then the second reflected ray from the second interface transmitted again, and then you will have third reflected ray. And this sometimes is called an echo series because it sounds like that the sound wave is reverberating through this layered medium, bouncing back and forth before it reemerges again as another ray. Okay, but this is called a ray series in optics. So let me move on to the next topic then, if you don't have any questions on this ray series interpretation.